we talked about what forces are and what they do, right? We talked about Newton's laws 1 and 2. And we're really, remember I said we're contracting forces in kinematics a little bit this year. So we're just doing these 4 to get started. We're just doing gravitational, and that means weight. You know, we did weight. And we're doing normal. We did normal to death on Tuesday. So today we're doing friction and tension forces, okay? So hopefully you got these down, and now we're going to do friction and tension. And then these are just things you do with all of them. We talked about this some already. Force components is from last week. You know how to take components. Free body diagrams, we did a little. And net force is for solving kinematics. We'll do a little bit of that. I think we did some of that. And today we'll end with a little bit of Newton's third law and action-reaction pairs. All right? And then we'll be done with forces. So if you're doing the reading, you can see how it sort of is scattered among 3 chapters in this book. But that's so the book can lay it out very clear, if you like things laid out very clearly. Okay? All right, so let's see. So we're going to start with friction. This is our next force in our little tour of forces here. Okay, so friction is a force. Spoiler alert, that opposes sliding motion. Notice I didn't say it opposes motion. I said it opposes sliding motion. And we'll talk about why I said it that way. Or the pent-up desire for motion. It depends on the situation. To solve problems, you have to understand pent-up desire. It acts along or parallel to surfaces. All right, so the normal force is pretty obvious which way the normal force acted, normal to the surface. That's why it's called the normal force. Perpendicular means normal. This one, the name doesn't give it away, but from your intuition, you may be aware that it is along the surface that you get it. Okay? So we're going to do, there's 2 kinds to keep up with. The first is static friction. So the 2 friction forces are very similar. One applies to things that are static, and one applies to things that are sliding. Okay, so static friction, the symbol we use is F, little f with an S, with a vector head on it, because all forces are vectors, as you know. And it's F between surfaces that are not sliding. Surfaces that are not sliding. And of course, that's what static means, okay? Now, notice I'm not saying moving. If you say this a little less thoughtfully, you might say it must be things that are not moving if they're static, but it's really referring to the 2 surfaces against each other. Right now, there's a static friction force between this block and this block. Okay? And if I slide this, now they're moving. But it's still a static friction force, isn't it? Right? Because these 2 aren't moving with respect to each other. Okay? We could do a definition in terms of moving reference frames and all that stuff. It's more fun just to say sliding. Okay? Between the block and the table is no longer static. That's sliding. But here I can accelerate the top block with static friction. Wow, static friction can cause motion. Okay? So just because it's static refers to sliding of the 2 surfaces that you're calculating it for. Okay? Let's talk about, let's do the block on a plane. Here we go. So we're going to say, let's tilt a ramp up like this, right, at angle theta, and think about a block sitting on the ramp like that. So we can do that here. I've got all my blocks today. Here we go. So there's a ramp, and here is a block sitting on the ramp, and it's being held in place by static friction. And I know you can't see it because everything up here is brown, but maybe there's a little bit of contrast, and it's not camouflaged completely. So if we were to think about the forces on this block now, we would say, okay, well, we know mg is down that way. That's always the case, and I drew it sort of at the center of mass because that's where it acts. We talked about last time there's a normal force pushing it up, right, that. Pushing it up, and last time we did some calculations and we figured out that the normal force is equal to the component of gravity this way, and the other component of gravity just slides it down the block, or I'm sorry, slides the block down the ramp. But it's not now, is it? There is a component of gravity pulling the block down the ramp, but it's not going down the ramp because of friction. There's also a force right here. This is a static friction force, keeping it from going down the ramp. Okay, that's why it's not sliding. If we're going to do a free body diagram, which of course we do, I highly recommend, we just think of the mass as a single little point. It's got mg down. It's got a normal force normal to the surface. I'm not trying to get the magnitudes right here. That normal force is a little big. And it's got Fs back, static friction back. So if you were going to break it into components and do a problem, you'd probably rather draw it like that. Right? Okay, so that's that. So now let's talk about how to define this friction force. Well, we just drew it. It followed the rules I said. It's along the direction of the surface, and it's opposing the pent-up desire for motion. It's back. Right? Which way does this want to slide? It wants to slide this way. It's this way. It's kind of easy to tell in this example. It wants to slide down. Friction pulls it up. Sometimes examples get hard to tell. Like, which way is the static friction on a tire when your car is speeding along, but it's not actually sliding against the road? That's hard to tell, right? So the way you figure it out is in your mind, you slowly turn off the friction and say, which way does it go? That's the direction of pent-up motion, okay? If you slowly turn the friction off of a tire, it would start to spin too fast. So friction actually pushes the other way. So the static friction force on a tire is actually forward. That's why the car goes forward. But here it's a little easier to see. If it wants to fall this way, the friction force has to be that way. But let's talk about the magnitude, okay? So now, what is the magnitude of static friction? Oh, no, it's not an equation, or it's not an equal sign. It's a less than or equal to sign. Less than or equal to mu s times the magnitude of the normal force. Right? Because it's always about two surfaces, so there's always a normal force to think about. So as long as you have a normal force, you have some static friction. And but then what is, that didn't tell you the value, right? That just said it's less than some value. So really the answer is whatever value needed, whatever it takes to avoid motion. But there's a limit from 0 newtons to, and then the maximum is the static friction coefficient times the normal force. Okay? So I mean, this mathematically clearly, you know, this means less than mu s times n, less than or equal to. It could only go down to 0. It can't be negative, right? You never have a case where the friction force pushes it forward. If you figure out how to do that, just let me know, because we'll be really rich, okay? But it can't really happen. So it's from 0 to mu s times the magnitude of the normal force, okay? So it's just some value. It's sort of like it's a constant, but it's not really a constant. It's a value that changes up to a constant, okay? So let's define, you know what the normal force is, you know what that force is. Let's define mu s is the coefficient of static friction. Let's talk about some properties of it. It's unitless. You can tell by looking at that equation. This is in newtons, this is in newtons. It's unitless. It's usually roughly a half, okay? Order of magnitude, it's a half, okay? It can't be below 0, or you would have, that'd be like a frictionless surface, it's 0. As soon as you have any friction, it starts to go up. It can be larger than 1. There's sort of a myth out there that, oh, it can't be larger than 1 because something about conservation of energy or whatever. Well, ask a gecko. It can be larger than 1, okay? So it's just usually most typical surfaces rubbing against each other. The static friction is about half the normal force on the surface, okay? But you'll do problems where we say it's 0.1, where it's 0.9, where it's 0.05. So when I say it's half, it's like usually 0.5 plus or minus 0.45, okay? So it ranges kind of between 0 and 1. All right, so now let's think about, are we sure really, though, that it could take different values here? So let's go back at let's think about that it can take different values. Forget the ramp, we'll do the ramp in a minute. Like let's see, what is the static friction force right now? It is actually 0, okay? To go sideways is 0. Why is it 0? Because it's whatever value is needed to avoid motion. So what value is needed right now to avoid motion sideways? You all do this. I do this. 0. Okay? It doesn't need any motion to avoid any force to avoid motion sideways because no force is being applied sideways, right? But if I push it now with my finger, I'm really pushing it. It's not moving, right? Now there's a static friction force that way. Is it equal to mu s times the normal force? No, it's less because I'm barely pushing it, right? It takes any value it needs to keep it from moving. But what's the highest it can go? Mu s times the normal force. What if I push harder than that? Oh, there it goes. Okay, it moved. Okay, so if it's not pushing, it's 0, bigger, 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 mu s times m. Right? And then that's as high as it can go. So I can take that whole range of forces, whatever it takes to avoid motion. Okay? Right now it's 0. Right now it is not mu s times m. Okay? That's just the maximum it can be.